This is a 2-speed constant mesh non-synchronous gearbox. The upper shaft is the input and the lower shaft is the output. The main gears are in constant mesh during the entire time, and it's the job of the orange slider gear or dog clutch to attach the output shaft to one of the output gears. Here, when the slider is engaged with the blue gear, we see rotation in the output shaft occurring. This particular setup gives us a 1.5:1 gear ratio, and power given to the input shaft is making its way through the system. Disconnecting the slider gear causes the output shaft to disconnect once again, and the gearbox begins to idle. Because this is a non-synchronous gearbox, the orange slider gear has some difficulty engaging with the green gear, but eventually, and with a little force, it will connect. Once attached, we are now seeing a rotation ratio of 3:1 on the output side. The input power is again flowing through the system. Detaching the slider once again stops output rotation. The design is fairly simple and straightforward. It incorporates wooden dowels and 608 bearings to help make things run smoother. Hot glue is used to connect any loose parts. The final product spins freely by hand. You can see the output shaft remains stationary when rotating the input side. Engagement of the slider gear is sometimes smooth and sometimes a little rough. Since there is such a large difference in rotation speed between the stationary slider and the rotating gears, it can be even more rough at higher rotational velocities. From this angle, it's easier to see the input and output shaft rotations. As we shift between high, low, and neutral points, the change of RPM in the output shaft is easily observed. Taking a close look at these slider gear engagement pins, it's easier to see why the shifting isn't always smooth. Oftentimes, these pins do not line up exactly with the holes, and other times, the friction between the pins and the gear can cause them to rotate together briefly without actually being engaged. Powering the input side with an 800 RPM drill gives us a better representation of the shifting quality. Occasionally it's smooth, while other times it will miss, causing the user to bounce or to force the shifting fork until it grabs hold. High-speed footage of the shifting engagement shows us exactly what happens during a smooth shift, as well as what happens during a rough one. If you're lucky, the pins and holes line up on contact for a smooth engagement, but if not, there's usually a little delay in getting them to connect. Applying constant pressure or bouncing the slider gear seems to help remedy this issue. Overall, this proof of concept model works great. There seems to be room for improvement when it comes to the pin engagement. I know that automotive gearboxes like this one use synchronizers to match the slider speed to the gears before they engage, and that probably helps a lot when it comes to shifting smoothness. I'm looking forward to testing this thing out in some different applications.